Alright guys, so this is going to be particularly for the people who were away on Antioch, because I know that you missed this lecture and we have a quiz this week, so I'm going to give you a walkthrough of what we covered and how to do the math. So the focus of this chapter is electrons, and the thing is that electrons behave very similarly to how light behaves, because light has properties of both waves and particles, and electrons also follow these laws of quantum mechanics. So we're going to do a little bit of an introduction about the behavior of light before we get into the behavior of electrons. Okay, so the first thing we're going to do is we're going to label a wave, and there are 3 variables that are involved, and only 2 of them will we really be focusing on in our class. So let's take a look at what a wave looks like. The first variable that we're going to be talking about is called wavelength. And wavelength, as you can see in the diagram, is the distance. Sometimes it's called the distance from crest to crest, although it doesn't have to be measured there. It can actually be measured if you look at it. Okay, so this is a crest and this is another crest. So that would be crest to crest. The tops, by the way, are crests. But it's the same distance that you would have, for example, if you started right here at the origin and went to the beginning of the next wave, including basically one crest and one trough, or you could also do it from trough to trough. So just to clarify, so these are crests. This would be a crest, this would be a crest. These are troughs down here. This would be a trough, and this would be a trough. Another thing that you definitely need to know is the symbol for wavelength. It looks kind of like an upside down Y. It's the Greek letter lambda. If you see that symbol, you need to recognize that that is wavelength. And the measurement for wavelength that we'll be using will be meters, although you will see a lot of times wavelengths, for example, when we talk about visible light, you're going to see oftentimes they're going to use nanometers. However, if it's given to you in something other than meters, you'll have to convert it in order to plug it into the equations that we use, because, for example, the speed of light is in meters per second. So if the wavelength is not in meters, it's not going to correlate with the speed of light, and then your answers are going to be wrong when you do your calculations. So the second variable in a wave is its amplitude. We're not going to be using amplitude in our class. It's not part of the formula that we're working with, but I did show it here labeled just so you knew what amplitude was. And then finally, the last one is called frequency. And frequency, we use the Greek letter nu. It basically looks like a V. And it's the number of waves per unit time. In other words, if we look at an entire wave, one crest, one trough, how many of those pass per second, that's going to be frequency. The units are going to be seconds to the -1 because it's waves per second, or in other words, waves per 1 second. But you may find it that it looks a little odd to put seconds to the -1. So another unit that we use is hertz. And so 1 hertz is the same thing as 1 wave per second. On the next slide here, I show you kind of a relationship between these. So if you notice, for example, here's our wavelength from crest to crest. The amplitude was the height. And then this one, if this was the same amount of time, let's say this was 1 second, and this was also 1 second, this one would have a higher frequency because more waves passed in the same amount of time. So if we take a look at the next slide, this sort of illustrates it a little better. So if we assume that the distance, the total distance that's shown here is 1 second, we could literally count how many waves passed in that 1 second of time. In our first one, we actually have 5. We could literally count out from here, that's 1, 2, 3, 4, and then 5. So there's 5 waves in 1 second, or that would be 5 hertz, or 5 seconds to the -1. The second wave has a shorter wavelength, but more waves pass in the same amount of time. It has a frequency of 10 hertz. So this is how you would write it, 5 waves per second, or 5 hertz, and the second one is 10 hertz. Notice that the wavelength and the frequency are inversely proportional to each other. In other words, as one goes up, the other one goes down. Not only that, but if we multiply wavelength times frequency, we get a constant, always. We always get the same number. So if one goes up, the other one goes down by exactly the same amount, and so this is called being inversely proportional. Now, the number that we actually get when we multiply them by each other, the number that we get is basically called the speed of light, and it's represented by the variable c. And so the speed of light is 3 times 10 to the 8th meters per second. And remember, wavelength was measured in meters, and frequency could be measured in seconds to the negative 1. So if we multiply meters times seconds to the negative 1, we get meters per second. And that's the speed of light. It's a constant. It does not change. Red light, purple light, ultraviolet light, X-rays, radio waves, they all travel at the same speed. What changes is the wavelength and frequency of the different lights, and also the amount of energy that they carry, which we'll get to in a minute. Okay, so that's a formula, and here's a sample problem that we worked in class. So let's just suppose that we have the question, what is the frequency of radiation if the wavelength is 2.40 times 10 to the negative 5th meters? Okay, so here's our formula. We know already our constant, and so for these problems it's going to be pretty easy because you're always going to be given one, you're going to be solving for the one that's missing. So every single time you're basically going to take the speed of light and you're going to divide it by the one that you have, and that will give you the one that you're missing. So this is this was the information we were given. We were given our wavelength was 2.4 times 10 to the negative 5th meters. If we rearrange our formula, we can divide both sides by wavelength and get frequency all by itself. It would look like this. I'm pretty lazy and I just plugged the numbers in, but this is the more appropriate way to do it, would be to change the formula first. That way when you plug your numbers in, you just solve. And so in this case, it's going to be 3 times 10 to the 8th meters per second, that's our speed of light, divided by 2.4 times 10 to the negative 5th meters, that was our wavelength. The answer we get is going to be our frequency, which we either need to include the units of seconds to the negative 1 or hertz. Now, for the purposes of significant digits, this is actually not done properly for significant digits, which brings me to actually a good time to point this out. So for the purposes of significant digits, if you remember, in multiplication and division, you base it on the number of significant digits in your original number. We're not using the speed of light as our determining factor because it's a constant. And constants don't count. Only thing that counts is going to be our measurements, and this was our measurement. So since this has 3 significant digits, technically our answer should have 3. So this is actually not perfect as far as the answer goes. It really should be 1.6 something, whatever that third number was, which got deleted. So just to point that out. Okay, the second problem I'm not going to work out. We did it in class, but in this case they're asking for the frequency, they're giving you the wavelength. You're going to do the same thing you did before. It's basically going to be 3 times 10 to the 8th divided by 6.25 times 10 to the negative 3rd, and that's going to give you your answer. I wanted to go through this next problem with you though, because in this case they're giving you the wavelength in nanometers, and this is going to be a common thing that's going to happen because, for example, visible light is measured in nanometers. But the problem is you cannot just plug nanometers into your equation and get the right answer because our speed of light was in meters per second. So the first thing we're going to do here is we are going to convert from nanometers to meters. Now I know some of you know that all you're really going to do here, and you know the kind of the simple way to do this is if you know that there's 10 to the negative 9th nanometers in a meter, then if you're going from nanometers to meters, you're going to move the decimal 9 places to the left. If you're going from meters to nanometers, you're going to move the decimal 9 places to the right. However, the proper way of doing this would be to set it up using dimensional analysis. So let me show you that. Okay, so I just showed here how you would work this out. So you're converting from nanometers to meters. We're going to put nanometers on the bottom. Our relationship is that 1 meter is 1 times 10 to the 9th nanometers. Here we go, nanometers is going to cancel. And so 670 divided by 1 times 10 to the 9th gives us this, 6.7 times 10 to the negative 7th meters. Once you've done that, now you go ahead and plug it in. That is our wavelength. And so we're going to take our speed of light, divide it by 6.7 times 10 to the negative 7th meters, and then your answer is going to be frequency, so it's going to be in hertz. for significant digits in this problem, since our original number has 2, then our answer can only have 2. In fact, technically I could get rid of the 0 right there and just make this 6.7. And in the previous problem, since our original number had 3, our answer could have 3. So that would be how to do a couple of practice problems. We did several in class, so if you need more help. And this slide is showing a portion of what we call the electromagnetic spectrum, and this is showing frequencies that we can see. Notice that remember that they are inversely proportional to each other, so that means the fact that this one has a smaller wavelength means it has a higher frequency. So if you've ever learned Roy G, Biv, red, orange, yellow, green, blue, indigo, violet, if you put those in order, then red would be your biggest wavelength. That would be the order from biggest wavelength to smallest wavelength. And it would be the order from lowest frequency to highest frequency. On the next slide, we have a diagram showing the whole electromagnetic spectrum. Let me get to it. Alright, and here you can see, so this is the electromagnetic spectrum, and it is showing us all of the different wavelengths of light. When we think of light, we think of what we can see. But that's only this tiny little portion of the electromagnetic spectrum. Gamma rays are all the way over here, and then X-rays, UV are visible light, infrared, microwaves, radio waves, and so on. If you look at these actually have the most energy. Energy and frequency are actually directly proportional to each other. So it's sort of the opposite of what wavelength was. So high energy equals high frequency, but smaller wavelength. And one way to think about this when you're thinking about the energy in light would be to think about ultraviolet light. We know that ultraviolet light is not good for you. You go out in the sun and it can cause skin cancer. Why can it cause skin cancer? Because it has a lot of energy in it, and that energy can penetrate your skin and it can basically cause mutations in your DNA. X-rays have even more energy, so they can penetrate soft tissue, and that's why an X-ray would show bone, because bone reflects the X-rays. It can't pass through it. But it can also damage tissues, and gamma rays are even stronger. And you may ask, well then, why are microwaves, why if you were to supposedly put something in the microwave, it explodes? And you put eggs in the microwave, they'll blow up, for example. Why in the world would a microwave make stuff get hot if microwaves are actually much weaker than even the visible light that we see? And really it has to do with the fact that microwaves cause water molecules to vibrate, and the vibrations are what heat up your food. So if you're heating, like a piece of plastic or a ceramic plate, the reason why they don't get hot is because there's no water. So the microwaves are not going to affect them, but they are going to affect things that contain water. And for example, in popcorn, the water gets so hot, it forms steam. That's what causes the popcorn to pop. You do need to know the order of light, which I believe is on the next slide. And you have this in your PowerPoint. So this goes through the electromagnetic spectrum, highest frequencies, the highest energy, like I said, and here's the order from our highest energy, highest frequency, all the way to our lowest. Alright, and to wrap this up, just to show you some of the different units that we use for wavelength. Remember I talked about nanometers would be one that you would definitely be encountering. Ultraviolet and visible light are measured in nanometers because of their size. But on the other hand, for example, microwaves and TV and radio waves, remember, have much larger wavelengths. So centimeters works well for microwaves, and meters works just fine for TV and radio because the waves are so big that you would be using normal numbers. So I just wanted to show that to you.